Research into graphene is booming. Since it was first isolated in 2004, there's been an explosion of academic research into this wonder material, resulting in over 50,000 peer-reviewed research articles to date. Over one-third of these were published in the last year alone. Governments around the world have recognized the strategic value of graphene and are investing heavily in its commercial and industrial development. The U.S., Chinese, and South Korean governments have contributed significant funding towards R&D efforts in both academic and commercial contexts, and the European Union has allocated over 1 billion euros to this effort over the coming decade. The fruits of this focused interest are already visible in the number of graphene-related inventions, which have been steadily doubling each year. In 2013, there were approximately 5,000 patents in graphene worldwide. Now that figure has exceeded 10,000. These inventions are spread out among research institutions located primarily in China, the United States, and South Korea, as well as major global corporations including Samsung, IBM, and LG Electronics. It is estimated that worldwide sales of graphene products are currently about 20 million. Extrapolating into the future with a projected compound annual growth rate of 44% will put this number at over $100 million by 2019. Present sales are mostly directed at R&D efforts, but as we will discuss later in today's webinar, coming years will see a number of commercial applications that capitalize on graphene's unique properties. Now, let's briefly discuss what is so special about graphene that gives it this singular set of extraordinary properties. There are a variety of natural materials composed exclusively of carbon atoms. For example, diamond and graphite. The difference between these substances lies in the way that the carbon atoms are bonded to each other. In diamond, each carbon atom is covalently bonded to 4 neighbors in a tetrahedral geometry. Graphite is composed of many layers where each carbon atom is covalently bonded to 3 neighbors. If we peel back these layers to a single sheet, what we have is graphene. The distinguishing feature of graphene is its honeycomb lattice formed by tiling hexagons of carbon atoms in a 2-dimensional plane. As with diamond, these atoms are connected by extremely strong covalent bonds with an interatomic distance of just 1.4 angstroms. But they are quite flexible and can be stretched in plane by up to 120%. Any unbonded carbon atoms are highly reactive, which means that a pure sheet of graphene is virtually defect-free, as you can see illustrated in the atomic force microscopy image in the lower left-hand corner. These features confer on graphene its amazing structural properties. The next feature to note is that each carbon atom in graphene contributes 1 free conduction electron. Due to the electronic structure of graphene, these electrons are effectively massless and can move through the material ballistically at 1/300th the speed of light, which is enormously fast. This feature contributes to graphene's unique electronic and thermal properties. Finally, a single sheet of graphene is extraordinarily thin, which explains why it is extremely light and virtually transparent. I'll now hand it over to Jeremy to describe some of these properties in greater detail.